later. So, basically what I drew here in black is the myosin. All right, so you have this desmin that's in the center, which is a bulge of protein. And we have that there, and it has two wings of the myosin. But we say that that's one molecule of myosin, okay? So that's the myosin. And if we go from here to here, from one end of the black to the other end of the black, that's going to be our A band, okay? Right, okay, so that's where the A band is. In the center, if you follow straight down, you'll see another line there where all the desmins are. That's the M line. So the M is within the A in that case. Does that make sense? That doesn't change. It can't change length at all. It stays the same there. Then we have the Z disc over here and the Z disc over here. Attached to the Z disc are actin. There's an actin molecule, there's an actin molecule. These are the thin bands. Now, the other thing I'll show you is the H band. The H band is where it's only myosin and the actin is not overlapping. See it here. So when this contracts, you're going to have the red going further in. Does that make sense? When it does, then the H band is going to actually change with contraction. And when it relaxes, it goes back the other way. Similarly, the I band is the areas where there's only actin without the overlapping myosin. So it's going to be at this level here to this level here. And again, when the myosin and actin, when they overlap each other, this black line will go further in, so therefore the I band is also going to change. So the only two that change is the H band and the I band. Does that make sense? It's confusing, and I would never, ever, ever, ever ask you guys to draw this on a test. One, it would probably take about 15 to 20 minutes and to label everything, and I don't want you to take those 15 or 20 minutes because you want to make it perfect so that I don't get confused, right? But I'm going to get confused. When I have to read only 10 of them, I will get confused when reading just one. Okay? It's not going to happen. But I will promise you there'll be a picture already on the test. This is lecture exam number 3. You'll have a picture of this, and I'll ask you questions about it. All right? So you can refer to it. All right? It won't be labeled. You might have to label it, or not really label, but you need to know what those parts are. Okay? Questions on that? I'll leave that there so you can take a picture of it later or during break or whichever. Okay? Any other questions about what we've talked about so far?
So the next exam has the muscle.
It's Arnold and the Scarecrow.
Right.
So it sounds like there's only two, but they're big topics. But most, I'll be honest with you, 30%, students have told me 40 to 50% of it deal with the action potential.
Oh, okay.
Okay? It's a lot. So how to apply the action potential. If you have too much potassium outside, what does that do to the action potential and so forth? And that's what we're going to talk about today. All right? So we kind of talked about the action potential, but there's two action potentials when we deal with a nerve and a muscle. There's an action potential of the nerve going down the axon. The neurotransmitter goes across the Delaware River and then turns on an action potential on the muscle. Now, there are a lot of similarities with those two different action potentials, but there's also there's a few things that are a little bit different, and we'll talk about those too. Okay? So most of this, I'm going to kind of whip through this, most of it, because we did action potential, but I want to spend more time on stuff we didn't get to. Okay? All right. So an action potential, it's a nerve impulse, that one jolt of electricity going through the axon can also go on the sarcolemma also of the muscle. The neurotransmitter is that chemical that leaves the axon terminal across the Delaware River and finds its receptor on the motor end plate. And acetylcholine is that neurotransmitter. But there are a whole slew of other neurotransmitters. We're going to go over about a dozen of them, but there's probably about 30 or 40, okay? So we have electrically excitable cells, right? All right? Muscle fibers and neurons. They're electrically excitable. We have that voltage. A lot of this we've seen before. There were kind of repeat slides I had in muscles. So you have this voltage, you have this electrical potential, and again, the membrane potential is that the membrane wants to go towards zero. Once it reaches zero, then there's not a potential, because you're at zero. So you need that driving force to push it towards zero. And the voltage is a difference of electrical charge from inside the cell versus outside the cell. The resting membrane potential in cells is somewhere between negative 90 to negative 60 millivolts, but our magic number that we're talking about, muscles and neurons, is going to be negative 70 millivolts. And it's just showing you from our salty banana, sodium wants to come in, potassium wants to go out. Okay? Leaky channels. As much as you want to keep that faucet extremely tight, you're going to have drips coming out. And sodium wants to come in because it follows its gradient from a high concentration outside the cell to inside the cell. Likewise, potassium wants to leak out. We have a lot more leaky potassium channels than we have sodium, and that's going to contribute why it's going to be a negative charge inside. Okay? An action potential, again, we're going to go sodium channels open very quickly. All right? We'll do this little chart thing for you again so you can visualize it. This is time. This is millivolts. Certain magic numbers we should know is negative 70, negative 55, 0, positive 35, and the other one down here, negative 85. Sodium channels are going to start opening. Remember, resting potential is at 70. We're going to have some stimulation. And when it does, if it reaches negative 55 by the sodium coming in, then we're going to have the sodium channel gates open wide, all the way, until it reaches about positive 35. This is called depolarization. It becomes more positive, or like I said, be careful with the wording, it's less negative. Same thing. Don't memorize, understand what it's doing. Then the sodium channel gates close very fast. And the potassium gates will open very fast. Potassium is then going to leave the cell. Potassium is a positive charge, so it's going to make inside the cell more negative. So it's going to start going down. We call this repolarization. The gates start closing for potassium around -70, but they close very slowly, allowing few different potassium ions still to leave because you're closing it very slowly. We call this hyperpolarization or an after potential. And it goes down, it undershoots to about -85 until the door is closed, and then it's going to go back to those leaky sodium-potassium channels, and gradually it'll go right back up to -70. Okay?
So the threshold is -55?
Threshold is -55. But we're going to talk about this area right here. Okay? This whole thing is an action potential. But this area here, the -70 to -55, is a crucial point too. It's called a local potential. So an action potential, positive going in, positive going out. Positive going in, positive going out. Okay? So you can do this on your own. It's basically showing you step by step. There's that. And you can see where it's going in. All of that. They call this reverse polarization. That's where the positive 35 is. Because it's reverse. It's going to go from sodium channels closing and potassium channels opening. Reverse polarization, they call that. Okay? And repolarization.
Is it 30 or 35?
I've seen it 30, I've seen it 35, yeah. I've never, yeah, that one we usually see, I've even seen positive 40. It varies, and that's it. But I've always seen -55. Never seen no. I would just stay with those. Up here, you'll see it in different things. Positive 30, positive 35, 40. Not much, I have never seen a positive more than 40. All right, so it just goes down this. And we talked about why it only goes one way, right? So it goes this way. And then behind it, we have this action, or the sodium-potassium pump, to put back the sodium-potassium where it came from.
Why does it only go one way?
The toilet bowl.
Oh, right.
Right? Okay. No, we'll go over that too. This is, we talk about myelination and unmyelinated. Unmyelinated neurons, they have to go through every part of the axon. It takes longer for that to happen. When it's myelinated, like I said, you go in the water and this is all covered, so you got to just try and swim forward as fast as you can so you can get up for air. You go in and you go underneath it, you can't get through here. So because of this, myelination, which is this area here, causes a very fast, we call it saltatory conduction, but very fast. It jumps. This is more so of how it actually happens. Every picture I've seen, they show it this way, but it doesn't go that way. It stays within the myelin. This is a better representation of what it is by these arrows. Okay? So the threshold, as sodium enters, it needs to go more positive. All right? And when it reaches -55, those sodium channel gates will open all the way, and you will have an action potential. If it reaches -55, it's the all or none principle. You will have, you will have an action potential. You will have the whole thing. There's no such thing as a partial action potential. Okay? And if you don't have it, we call it subthreshold, and it doesn't fire an action potential. You either have it or you don't. The all or none principle. Okay? Subthreshold versus threshold. Okay? The strength of the stimulus is encoded by the frequency of the discharge. If we have more frequency, more stimulus over here, then the action potential is going to fire faster. It's not going to be a stronger action potential. You can only reach positive 35. But you can have them closer to each other or farther from each other. It's the frequency that makes it sound like there's more power to it. Okay? So the stronger the stimulus, the greater the frequency of action potentials. Yep.
So in a muscle, acetylcholine is what starts an action potential in the muscle.
In the muscle.
But so would you say the stimulus is what starts it in the nerves, or what
Mhm.
starts, is that?
Yeah.
Okay.
Whatever the dendrite of another neuron is going to tell it to do.
Uh-huh.
And we'll talk about all those dendrites that are, we'll get into it. We'll get into it. Okay? Question?
Yeah, just really quick. You said like for R or non-sensible, like if you don't have a clip sub what?
Subthreshold.
Oh, okay, sub.
Subthreshold.
Gotcha.
All right? So if it doesn't make it to negative 55, it's subthreshold. Threshold point is a, so if it's less than negative 35, I'm sorry, negative 55, you're not going to have an action potential. Okay? In fact, I might as well just tell you right, in here, this is called a local potential. We'll talk about it. God bless you. This can go up and down, depending on the stimulus. That's what makes this a little bit different over here. But once it reaches negative 55, it's all. So it depends on, you know, if you go like you're pressing and let it go, pressing and let it go. As long as it's not making up to negative 55, it can go up and down. Okay? And I'll show you a few other things on that. And the refractory periods, think of the toilet bowl, right? You get an absolute refractory period where you can't fire another action potential until it reaches negative 70 degrees, or negative 70 millivolts again. All right? So if you put a stimulus here, 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 you're not going to fire another one. If you do this, it's not going to be a higher one. If you do this, it's not going to be another one. It has to reach negative 70 to do that. It's in an absolute refractory period. However, a relative refractory period is that it's basically during this time here, during the hyperpolarization. If you have a strong enough stimulus, you could get it up there. You're going to have to go from negative 85 to negative 55, but if it's strong enough, you can do it. Okay? And it's showing this picture here.
Because relative refractory periods, does it happen a lot? Or
If it's strong enough, it depends on what it is. It could be a certain smell. It could be a lot of different things. You go through life going through it, you just don't realize what's happening. Okay? Restoring the resting potential, restoring the electrochemical, we have this sodium-potassium pump that's going to do this. We got to put the charges back out there. We got to get it back to negative 70. We need to put the sodium in the leaky channels. We got to get it back over there. Otherwise, it won't be leaky anymore. They won't be coming in. If you have, just give me numbers. If you have 5 potassiums inside and 5 potassiums outside, we're at a halt. It's not going to do anything. There's no gradient. So we got to have one side more. So we have the sodium-potassium pump that's going to fix these things. Okay? Now, the local potential, this part right here. Few things on this. Could be a lot of different things doing this. It'll go up, it'll go down. It'll go up, it'll go down. Depends on the stimulus. Certain chemicals can do that. Light, heat, mechanical disturbance, pressure, stretch. So many different stimuli that can do this. It will open up sodium gates to stimulate it, or it'll close them. It'll go towards zero, i.e. we got depolarization. So if I got this bigger, depolarization, repolarization, depolarization, until it reaches negative 55. You put pressure there, more sodium will go in. When the pressure is released, it closes. Right, that's one way. I mean, light could do something, chemicals could do something. Whatever the stimulation is, you smell roses, no problem. You smell pizza, no problem. You're in the septic tank, you'll be vomiting. It's going to stir up your vomiting center. Too much pressure, too much chemicals are going to stimulate something. Sodium diffuses for a short distance, then travels towards the trigger zone. All right, it starts to depolarize. It's going to go up towards zero. They're graded. They could go up and down. They're not all or none. It could go down. It could go up. Once it reaches negative 55, that's the all or none. Okay? And less than that is sub-threshold. So differences between the local potential and action potential. Local potentials are graded, as I just said. The stronger the stimuli, the more sodium gates will open. They're decremental, meaning they get weaker farther from the spread of stimulus. You put a needle over here in my arm, around this area, they're getting stimulated. I feel pain over there. As you go further away from it, I don't feel the pain where my hand is. Does that make sense? It loses its stimulus further from the point of where the stimulus is. It's reversible. Could go down, could go back up. And again, it's either what we call excitatory or inhibitory. Excitatory, it'll depolarize. Inhibitory, it'll hyperpolarize. Or, I'm sorry, hyperpolarize. Did I say repolarize last time? Yeah, I did. Well, it's hyperpolarize. All right? It's going to go towards negative 85 further now. Okay? It'll want to do that. All right? So, just showing you that chemicals can do this. Okay? So the local potential is this area right here. And it's just showing you resting potential, if you follow it over here, and so forth, doing a whole action potential. But you could see this when you're at home. It's better to see on the screen. Blue dots, I think, of potassium, and is it? Yeah, doing that thing. So again, this is showing you different, now it's verbalizing it for you, which part does. All right? So let me ask you this. Let me see some check it here. I'm going to just make sure I'm not. Okay. So let me ask you this. If we block sodium channels with a certain medication, what will that do to the action potential?
Wouldn't it slow it or not happen?
Yeah, it wouldn't happen, yeah. That's how lidocaine usually works. Lidocaine is a pain medication that we give by needle, but you can give it as a patch. Lidocaine is going to block sodium channels. So what will happen is, it's not if you have a pain area over here, I stick a needle in here, it's going to send an action potential going into my spinal cord and going up to my brain, and realizing that's pain, I'm going to say, ow. But if we put lidocaine here and block sodium channels at that localized area, you're not going to have an action potential going towards your spinal cord and up. So you're not going to feel any pain, although we're doing what we need to do. You see what I'm saying on that?
Isn't it still a needle, though?
Yeah.
Like, so...
But you don't feel the pain, it's numb,
Oh, that's cool.
right? I mean, if you think about it, so it won't fire an action potential going up to your brain. You're blocking it, temporarily. What if this is what I mean by applying it. What if I gave a bolus of potassium in your bloodstream? So outside your cell is tons of potassium. What does that do to the action potential?
Does that pause it also? Want to make it happen?
Yeah, require more.
Okay, normally we have more potassium than inside than outside. Does that make sense?
Mm-hmm.
But now we're reversing it. Now the potassium is going to be more on the outside than the inside. So does the potassium want to go out?
No, let me go in.
Stay in. So inside, is it going to be more positive or more negative? Or positive. So you're going to fire an action, but this negative 70 is not going to be negative 70 because it's going to be loaded of potassium inside. This negative 70 is going to be much higher. And what's going to happen is you're not going to be able to fire another action potential because this one's still in a sustained action potential. It's still in its refractory period. This is why you don't give a bolus of potassium to someone. This is probably the worst case scenario. Of all the electrolyte imbalances we have, this is the one we're most concerned about. Hyperkalemia. It's Ka, that's where the potassium with a K comes in. When you have a lot of potassium in your bloodstream, you're not going to be able to fire another action potential, let's say, of your heart.
But you can still fire one?
It'll be up there. You can't fire another one.
Okay.
That first one is still in an absolute refractory period. It's not going to allow you to do another one until it reaches negative 70, but it never reaches negative 70. This will give you a heart attack, cardiac arrest. The organ that's going to get rid of the potassium is the kidneys. And if you have kidney failure, you're going to build up your potassium in your bloodstream because you can't pee it out. And they'll die of a heart attack. So when you have renal failure, we're not going to allow you to do that. We're going to put you on dialysis. And it's basically a kidney outside your body to get out that potassium. What happens if we decrease potassium in the bloodstream?
It make it harder for another action potential because it becomes more negative inside the cell. Did I go too far?
Where did nothing come?
The potassium wants to come.
Well, let me ask you this. Normally, do you have more potassium inside or outside the cell?
So I want it to leave.
Right, but normally, do we have more potassium outside or inside the cell? Inside. So if we remove more potassium on the outside, is that going to do much to the cell?
More so want to leave.
More would probably want to leave, but it isn't going to really do much, though. Does that make sense? It's still going to go from a high concentration to a low. It goes at a certain pace. Very little. Very little. But it really isn't going to do much because it's what it's supposed to do. So we don't see much with hypokalemia. What about a, go ahead.
What about a lot of sodium?
Yeah, if you put too much sodium on the outside, hypernatremia, so you have more sodium on the outside, is that going to do anything to the action potential?
Make it more sensitive, like
Yeah, like what Antonio's saying, to make it a little bit more sensitive, but in essence, it really isn't doing much though, because that's the way it normally would be. What about hyponatremia? In other words, a decrease of sodium on the outside.
Then the sodium that's in the cell wants to leave, then what I was talking about.
Right. Now, sodium wants to leave the cell.
Rather than come
So
back.
you're not going to be able to do an action potential. Does that make sense?
Or
Which is
require-
basically blocking sodium channels. I mean, it's going to give you the same effect.
Does it block it, or does it just require?
No, it doesn't block it. It's just not going to go that way. It's not going to, I mean, it's going to leave the cell, if anything.
So in order to have an action potential, you need a very strong stimulus, because it would be more negative in?
Say that again?
You would then need a stronger stimulus?
Yeah, but it just
So
won't.
it would be more negative?
Yeah, but you can't, because there's too little sodium out there. Do you know what I'm saying? Because it normally would have sodium water coming from the outside to the inside. But now it's going to go from the inside to the outside. So what's going to happen is this is going to be lower, the resting potential. So you're not going to fire one. Or I see what you're saying. You need a stronger...
A stronger...
Yeah, you would need a stronger stimulus to do that. Because it'll probably be even lower than 85. Mm-hmm.
Because it would still have to reach 55.
It still has to reach negative 55, yep. Mm-hmm. Now, what about if we if we open up chloride channels? Chloride channels. Which way does the chloride want to go now? From the outside to in, or the inside to out? Right. What is that going to do to inside the cell? More positive, more negative?
More negative.
More negative. So again, it's going to be difficult to produce a action potential. Do you see how to apply this kind of stuff? I got a couple questions on the review questions, but it's about applying this stuff.
Is there any difference between blocking sodium channels and blocking potassium channels? Would they have the same result?
No, but there's medications that will do just one and medications that do the other. And the side effects, because potassium channels are on other things too, so you don't want to cover them all. You want to see if you can try and get it in a localized area. But yeah. All right, see how you're using this? It's ticking it up a notch, but it's, if you understand those, then I know you understand the action potential, and you can see how to apply this stuff. Okay?
So normally chloride's on the outside?
Mm-hmm.
Right.
The salty banana.
Right.
Mm-hmm. Okay? All right. So synapse, right, where the neuron touches the muscle, right? And again, a synapse versus a neuromuscular junction. A synapse is a nerve to a nerve or a nerve to a muscle. A neuromuscular junction is specifically a nerve to a muscle. So all neuromuscular junctions are synapses, but not all synapses are neuromuscular junctions. All right? Just nomenclature. Okay? Any neuron that releases acetylcholine is what we call a cholinergic neuron. We're going to use that quite often when we get to the autonomic nervous system. So cholinergic neuron is a neuron that will secrete or release acetylcholine. All right? So again, just as a review, the action potential comes down the axon to the axon terminal. This is New Jersey, Delaware River, Pennsylvania. Odd geography, just deal with it. Okay? Someone will have a list for me when I die. Okay? When the action potential reaches the axon terminal, there's calcium that's located in here, and when the action potential gets down here, it opens up calcium channels, allowing calcium to come inside the axon terminal. This changes the charge inside, and it will bind to, the calcium will bind to these vesicles that contain neurotransmitters, i.e. acetylcholine in this case. Acetylcholine is the green balls. Once the calcium binds to the vesicles, then the vesicles will fuse to the presynaptic membrane and release the acetylcholine across the synaptic cleft, across the Delaware, until it reaches the acetylcholine receptors on the motor end plate. That sets up, that allows the sodium, because it's basically, it goes on here, but once it hits this receptor, it opens up sodium channels, allowing sodium to go in and creating this action potential on the muscle. If this is staying there the whole time, you will always have a contraction. So we got to break this up, and that's what acetylcholine esterase, or just cholinesterase, is going to break up this acetylcholine into choline, which gets put back into here, recycled to make more acetylcholine, and acetylcholine breaks up to choline and acetate, or acetic acid, which is all over your body. So it just floats around here and just mixes and mingles with the acetic acid all around your body anyway. Acetylcholine esterase, its main job is to take this acetylcholine off of this to stop this contraction from happening. Otherwise, it'll stay like that. So, everything I just said, action potential goes through the nerve axon to the axon terminal. Depolarization occurs at the presynaptic membrane, allowing the calcium channels to open, putting the calcium into the axon terminal. Calcium binds to the vesicles, which have acetylcholine, and then these vesicles fuse to the presynaptic membrane and release the acetylcholine. The acetylcholine binds to the postsynaptic membrane of the muscle. This is what's causing the local potential at that area. The more acetylcholine, the more this is going to go up. Muscle action potential spreads across the muscle membrane, and the action potential goes down the T tubules. Action potential gets close to the sarcoplasmic reticulum, and that's where it's going to allow calcium to come out. Meanwhile, acetylcholine esterase is going to start breaking up some of that acetylcholine so that we can break up the contraction when it needs to. The numbers here correspond to the numbers that I just put. And you can follow it all over here. You can see it over here too. There's the axon terminal, the synaptic cleft, presynaptic membrane, muscle. Okay. Again, just so you can visualize it, this is a sodium channel, so to say. Sodium can't get in here, but as soon as acetylcholine goes and binds on here, it opens up the gates. As much as you can't get into this room unless I unlock the door. Okay? And we talked about a lot of different things that would result in flaccid paralysis or spastic paralysis. Black widow spider, myasthenia gravis, botulism, and so forth. Okay? All right, transmission types. We kind of talked about it in this way here. It's either depolarization or hyperpolarization. anything that's going to cause depolarization, we call an excitatory postsynaptic potential, or EPSP, okay? So it's going to cause it to become, go towards negative 55 to create an action potential. That's what it wants to do. So it brings it closer to threshold, an EPSP. So this is the depolarization going on. We also have an IPSP, and this is the opposite, okay? It's more negative. It's going to bring it down closer to negative 85, right? So further from threshold. So we could do that a few different ways. We could either open up chloride channels or opening up potassium channels. Think of the charges. Think of where they are, salty banana. Okay? So that's an EPSP, IPSP, just up and down. Then we could have this, and the picture would be worth 1,000 words on this. Then you could have a presynaptic modulation. Ooh, big word. This is where certain things could this is going to release acetylcholine across here to get it to its receptors. But we can modulate how much this can occur by having another neuron on here. We could have this neuron stimulate it, we could have this neuron inhibit it. It gets complicated now, but not too hard, not that you can't understand it, just making you appreciate how complex this is. A neurotransmitter could be released to inhibit it. Endorphins is a type of neurotransmitter that maybe this one is going to release. So here's the presynaptic membrane, postsynaptic membrane in this case. And this could say we wanted to stop this from releasing acetylcholine over here. Endorphins inhibits pain sensation. These are your natural high kind of neurotransmitters. You're running a marathon and someone puts a needle, it punches you, you really didn't feel it. You feel something, but you don't feel pain until later on. These are your endorphins that are going to stop the pain from happening. And it usually occurs with exercise. We could have this presynaptic facilitation. And it will increase the neurotransmitter release. A good example of this is glutamate, an excitatory. It will enhance nitric oxide release, and this will actually make your blood vessels dilate even more. This thing I drew in green is what we call a modulating neuron. It's going to modulate this neuron by this neuron. Does that make sense? Like this. Without this firing, this is going to produce a lot of acetylcholine here. But we could have one where it's going to modulate and say, if you're going to inhibit this from releasing all that acetylcholine. It'll slow it down. These are the neurotransmitters you need to know. There's about 12 of them. Acetylcholine, epinephrine, norepinephrine, substance P. All of these could be excitatory or inhibitory. It depends on where it is, and we'll talk about it throughout the nervous system. These are the abbreviations for those. Substance P is our pain neurotransmitter. When you feel pain, it's going to release substance P in its synaptic cleft. That's what's going to give you pain. Substance P. I think that's what the P stands for. Maybe not, but that's how I remember it. These over here, dopamine, serotonin, histamine, glutamate, aspartate. All of these are excitatory. These will all cause EPSPs. These, we call it GABA. Much easier to say. All right? Know what is this, okay? GABA, glycine, and endorphins are inhibitory things. GABA is the most abundant inhibitory neurotransmitter we have in our body. It's all over the place. And there's medications that are out there that are going to either stimulate more of these neurotransmitters or inhibit them. Okay? To give you an example, once you know a little about neurotransmitters, depression is due to a decrease in norepinephrine and serotonin. So guess what? The treatment for depression is that we need to increase norepinephrine and increase serotonin. Prozac is what we call an SSRI, a selective serotonin reuptake inhibitor. What the heck does that mean? All right. Let's just use this as an example. This is serotonin, and this is another neuron. Okay? In depression, this is not firing this neuron, and you're not getting stimulated in the mind. You're getting depressed. That's how it's presenting. Okay? It's more complicated than that, but I'm trying to make it simple for you to understand. So what happens here, the Prozac, it's going to, if this is going to be your serotonin, normally they need to, as you've seen before, they're going to go back in here and make more. But what's going to happen is, it's called an SSRI, a selective serotonin reuptake inhibitor. It's going to it's going to inhibit the reuptake, allowing the serotonin to stay here for a longer amount of time. You're going to increase the amount of serotonin in the cleft by doing that. And with that, you should be making the depression go away. I mean, that's the theory on it. I wouldn't ask you about that, but I'm just trying to show you, if you understand this now, when you get into pharmacology and many of your classes that you're going to be having, because most of you are going into medical professions, you're going to go back to this stuff, and you need to understand how this stuff works. Parkinson's is a decrease in dopamine. So we're going to do medications to try and increase dopamine. But as I told you before, anything to do with the mind, even these Prozac and stuff like that, you have to build it up because we have that blood-brain barrier. It's difficult to get medications into the brain. So they have to give you bigger doses, or you're going to see a change maybe after 6 to 8 weeks. It's not going to happen in 1 week. But look at this. If we increase the amount of dopamine, that's good. Parkinson's should go away. However, there's a very small window. Because if we give you too much dopamine, an increase of dopamine can cause schizophrenia. So the treatment for schizophrenia is to decrease dopamine. And when they're if you give too much of it, they're going to start doing this. It's a fine line. It's hard to control. So again, I'm not going to ask you questions on that, I'm just trying to make you appreciate, don't forget this stuff, because you're going to be, I guarantee, especially nurses, you're going to deal with pharmacology, you're going to need to know all this kind of stuff. And instead of relearning this stuff, I want you to just review it. There's a big difference between relearn and review. So, at least you have an idea of steps ahead. Okay? All right, so summation of synapses. We have spatial summation, and this is many synapses arrive to cause one trigger zone to occur. I'll show you what I mean by this. Or we could have temporal summation. Basically, think of, and I hate to be so violent with you, but for some reason, these are the only things that are popping into my head. If I have one person over here, and I have 20 people giving one punch on them, they're going to feel a very major pain. All right? One punch is just not going to do it. But when you have 20 at the same time, it creates, it's higher. That's what we call spatial summation. Many synapses arrive at the same time. Bam! And that could actually build that up to a negative 55. When you have a lot of neurons doing that. Or we could have temporal summation, and it's done by one synapse, but now you're thinking of this guy, and we're just taking one punch, but we're giving you 50 punches in sequence. That's going to build up the same amount of pain as though 50 people punched on you. Does that make sense? We call that temporal. It's a pulsatile thing. So you could have, they're just showing two here, you could have two neurons going on here that can cause the action potential to begin. Or you could have a brigade, you could have only one neuron there, but the frequency on that one can cause an action potential to occur. See the difference? Right? Okay? What we've been showing you over here. All right? It's not spatial, this would be temporal. It's one that's going boom, it's going right after the other. If it was another one, it would go like this and go up, maybe getting higher and higher. This is what it looks like in real life. All right? You could have tons and tons of different neurons going on one neuron. Some of them are inhibitory, some of them are excitatory. If you have 100 inhibitory and 50 excitatory, the sum of it is that you're not going to be able to fire anything because the inhibitory ones win. If they're firing. So it could get very complicated. Okay? All right. Neural circuits. To go with this type of thing. Because this is really showing you that and each one of these is an axon terminal here, an axon terminal here. But this is, they cut it, but this is an axon of another neuron, an axon of another neuron, an axon of another neuron, and so forth. Does that make sense? They're just showing the ends of them. And each one of these axons, some of them are hitting, you can see that this blue area here is a dendrite. Some of them could go on a dendrite, some of them could go on a cell body, some of them could go on the axons. So that's what this next part is, the circuits of this. Synaptic stations, where we could have inhibitory, excitatory, and a bunch of things happening. There's three that we could do. The axon could go to a dendrite, an axon could go to the cell body or soma, an axon could go to another axon. So we could have axodendritic, axosomatic, or axonic.
Those are all stations?
They're all, right, so you could have a neuron that could go to an axon, a cell body, or a dendrite. Very simple. All right, and that's what those mean. Each one of those is a station. Now, once you understand that, then we could have different things going on. Negative feedback. Depends on if it's inhibitory, excitatory, right? So they're showing positive as excitatory and negatives as inhibitory. So if this neuron is going to tell that neuron what to do, we could actually have negative feedback. If there's too much positive going over here, it could say, whoa, we need to slow it down, and it connects to the cell body. You see that? So that's negative feedback. We could slow it down if there's too much impulses going on. We could do lateral inhibition, where we could have certain things over here, going laterally, so one neuron could actually tell other neurons what to do like this. All right, and that's something we call fine touch discrimination of 2 points. What the heck does that mean? I'll tell you. Certain parts of your body can do this, certain parts can't. They're more sensitive. If I take 2 pencils together like this, okay, I touched it just like this, I touch it on my back, I'll tell you that I can feel it. But to tell you the truth, if you do this or you do this, I'm going to tell you it's 1 point. I can't tell there's 2 points there or not. My back is not that sensitive. But if I do that on my lip, I can tell you the difference. You see what I mean? There's certain parts that are more sensitive. We call that being able to do fine touch discrimination of 2 points. Certain parts of your body can do that, and that helps the medical professional that say, you're supposed to be able to feel 2 points. If you can't, there's something going on with the nervous system. Convergence. You can see where many neurons could actually converge to one. That can happen there too. Divergence, the opposite. One nerve can go further out, similar to that. Reverbatory. Positive going this way and make it stronger and stronger and stronger. Positive feedback, so to say. And then you've got this crazy mess, and I really don't want to explain it. It's self-explanatory. You could have a big mess going on here. Okay? That's it. Okay? I'll give you guys a little break, but I want to start the next one, not too heavy. Let me just, before I give you a break, spinal cord, yeah, I think I'm going to do the first 38 slides. So that shouldn't take maybe like 45 minutes. And then the rest of the time, just have you look at bones. Okay? So, lecture exam number 3. When is that? Monday? Okay. That's going to be Arnold and Scarecrow. Not this Superman. Okay. Arnold and Scarecrow. I would say about 50% of the exam, 40 to 50% is going to be action potential stuff. You could see, for a bigger part, if you look at it, half of the muscle and half of the nerve of Scarecrow is about action potential. And there's a strong overlap between the two. You also have the neuromuscular junction. There's a strong overlap between the two. Like I said, from here on out, they're usually the lecture exams have something to do with each other. I created it in that way. I just want to share something with you. I'll let you guys take a break. Okay, this is my urology, and I don't have it for you guys, but just so you could, we go over it in urology actually. So hyperkalemia, if you increase the potassium around the outside of the cells, that means there's a decrease of potassium leaving the cells. You agree with that? Which means the intracellular fluid remains more positive, and the action potentials cannot repolarize, leading to no muscle contraction. Do you understand that, how it's going step by step?
Wait, what PowerPoint is this?
It's not, you don't have it.
Oh.
I'm debating about putting it in for you guys. I mean, verbalized it, but it gets heavy in A&P too. And we talk of things like edema, and if I'm going to put it in there, I can't put those other things because we never talked about that. So you get cardiac arrhythmias, and that can cause cardiac arrest. Elevated T waves, you won't understand that. That's the EKGs. Hypokalemia, a decrease of potassium, and the cardiac arrhythmias, you can occur, but they're not so extreme that you're going to have cardiac arrest. We could see certain things happening in the EKG. So this is what's happening over here. Normal kalemia, all right, if you want to call it that, right? Normal kalemia, normally. The potassium wants to leave the cell, okay? Because you have more potassium inside than outside. It normally wants to see there, but it gets leaky. So right at this point, the resting membrane potential is, when it's closed, it's going to be stable, right? It's going to be stable. Now, if you have hyperkalemia, we're going to put a lot of potassium on the outside of the cell, so it's going to flow inside the cell, because it's going with the gradient. So there's going to be less potassium leaving the cell. Does that make sense? So that means that the resting membrane potential is going to be higher than the negative 70. It's going to be more positive inside. So as that is, the cells are, what you were saying, are more excitable. Because it only has to go from, I'm just giving you numbers, you're going to go from, let's say it moves it up to, I don't know, let's say negative 10. So now just a little bit of potassium, it's going to fire an action potential. You don't have to, you know what I'm saying, it's already up there, it's already high. So it's already at an action potential. So it's really excited at this point.
So more action potential?
Well, it stays as an action because you can't repolarize.
Oh, okay.
So it's excited, it's overly excited. Then in hypokalemia, this is more of a natural thing, though. Not natural, but it's more of an exaggerated normal kalemic state. You're just going to have less out there, but we have less out there anyway. So they're saying that there's going to be reduced extracellular fluid, which is a greater diffusion. It's going to pour out a little bit faster than usual. So you're going to have a lower amount of the resting potential will be lower than what it is, because it's going to pour out a little bit more. But it's not so great that it's going to cause a cardiac arrest. We see it, but we don't see it as drastic. We can put more potassium in there. So the cells are less excitable, because the number, I'm just giving you numbers, instead of negative 70, it's like negative, that's what I'm saying, it's not much of a difference. It goes from negative 70 to maybe a negative 75. It's not a drastic thing that we see, because it naturally wants to do that. So it's less excitable. It's going to need more amount of, that's what they're saying, going from negative 70 to negative 55, now you're going from negative 75 to negative 55. It's less excitable. You need to put more power, more stimulus on it for it to happen.
So your patient is hypervolemic, but not maybe so much so that they're going to go into cardiac arrest.
Correct. There may be arrhythmias, you might skip a beat or something, but it's not going to cause it
Visibly,
to
are they
stop.
going to display some symptoms?
What's that?
Visibly, are they going to display some symptoms? You can't.
Not really. Dehydrated maybe, something like that, but it's nothing that's, I mean, they might get a little constipated because you have smooth muscles around your intestines. So that's going to be slowed down also. So therefore, your contractions of the smooth muscle is not going to contract good. It's going to contract slower because it's less excitable. So it's these vague kind of symptoms that you probably wouldn't see. You're constipated. It could be eating a lot
Does
of...
it include things like more sensitivity to pain?
No, I don't see it much on that. I don't see it much on that. All right? Does that make sense about this over here? A little bit more?
Would you, I mean, if you ate a lot of bananas, would you have a heart attack? Like, is it like that? Or,
No, the reason why is because you have good kidneys.
oh, okay.
You could drink a gallon of salt water. I wouldn't do this at home. But you could drink a gallon of salt water, and your kidneys will get rid of all that extra salt, because that's the job of the kidneys. But the problem is with kidneys, not really a problem, it's actually really good, you don't have any symptoms until it reaches 80% of renal failure. So if you have a slight renal failure that you don't know about, you haven't had your blood test done, you might have like 30% your kidneys are shot, but you don't even know it because you don't show any presentation. That's why I don't encourage you to drink a gallon of the salt water, just in case you have that suboptimal or subacute kind of condition. But if you're healthy, drink a gallon of salt water. You're going to get rid of it. That's the job of the kidneys.
Go get your labs done first. Just get your labs done first.
Get your labs done first. But still, why would you want to push your, All right? Questions on that? And then we get into urology is probably students, in AMPT, that's the worst one. Because it brings back miserable memories of chemistry. But
I think it is kind of.
Yeah, it's bringing back everything. Calcium from bones, and you got the hormones coming back, and I mean, I like it because it puts everything together, but if you haven't been paying attention with each one of the systems, then it's like, you might have to go back to that? Yeah, you gotta go back to it, so, hypokalemic and stuff. And I teach a little bit more than other teachers, where I talk about hypokalemia and hyperkalemia, so when you hear this for the first time, it won't be your first time. Students usually come back to me and say, Dr. Gamaro, first off, I don't get any thank yous during the class. Never, okay? It's usually 2 years later when they realize what I did. They usually see themselves, they're struggling in their nursing program, but when they look around at other students, they're not struggling like the other students are. And then you find yourself teaching these other students to reinforce it for yourself, and you talk about hypokalemia and hyperkalemia, and like, oh, this is what's happening, action potential wasn't taught to me like that. That's what I mean. I'm getting you prepared for those, if you're exercise physiology, I expect you to know action potential and how to apply it. So I'm putting that all out there for you. It's not, and as you can see by my exams, it's not just make sure it's not just know the action potential, but how to apply it.
Could you send us a couple of slides?
Yeah, but I'm going to have to tweak it up because, I could also put in, like the sodium, which I didn't do for you guys, like hypernatremia. You have an increase of sodium in the blood. This is where, hypertension. So you have this increase of water in the extracellular fluid, because if there's more sodium there, it's concentrated. It's like taking lemonade and you're drinking. It's really bitter, because it has a lot of crystals in it. So you're going to put more water there, so it's more dilute. So you're going to put more. So when sodium goes into your bloodstream, when you eat like a wonderful McDonald's salty burger, it's going to go into your bloodstream, and it's going to make it more concentrated. So then water is going to leave your body cells to get into the bloodstream to dilute that. If you do that, you increase the blood volume, which means you're going to increase the blood pressure. That's why you don't want to have a salty meal if you have high blood pressure as it is. But then the extra fluid has no place to go, so it goes in between the cells, and that's what causes edema. I mention that only because, I don't know, I got to figure out how I'm going to put it for you guys, because I don't want to throw in words like edema and all this, because it won't make sense. You know, and hyponatremic, if you decrease sodium in your blood, then you're going to have hypotensive, and usually faint. So if someone asks me, like, let's say Antonio over here, he says to me, there's something wrong with my sodium, can you guess what it is? If it's just sodium, I could just look at him or ask him to do something, and I could tell you right away what it is. I could look at his feet, I could look at his body, and if they're swollen, he has hypernatremia. He's got more salt in his body because I can see he's bloated. I ask him to stand up, he faints, he's got hyponatremia. I mean, there's other reasons that would cause that, but if he comes up to me and says, there's something wrong with my sodium, that's an easy exam that I can do. So, I'll try and adjust that later tonight, and by tomorrow when we see each other, I'll try and put that down. There's also something that a student made for me. Was it last semester? He actually made it for himself, and he passed it out. Thought it was good. I mean, you should make it yourself, but I'll show you where is it? I need this chart. Here it is. If you block sodium channels, what will that do? If you increase sodium permeability, what does it do? Well, maybe I'll give you that too. You want it? Yeah. Block the potassium channels, what does it do? You can almost use that as he used it as a flashcard thing, where he did this and he cut them and he folded them in half or whatever. If you block the potassium channels, can you predict what it's going to do? Increase this, what is it going to do? So, that's something he put together. Yeah, why don't you take a break until 7:30. Actually, what I'll do is I'll just make a copy of this and print it out for you guys. Any questions at all, or?
So which PowerPoint is this one that you said we had to have read?
Frankenstein, but that won't be for lecture exam number 4. So that is Intro to Central Nervous System,
So
CNS.
that's for exam 4?
Correct.
Okay. So what?
It's only about 60 slides. It's a short one, very short.
Oh, it's a Frankenstein. So what other PowerPoint are we doing today? Which other?
Oh, Superman, spinal cord.
Okay.
And I'm going to do like the first 38 slides.
Okay.
Yeah. So let me go print this out for you guys. I think that's it, yeah. Down the wall.
Oh, yeah, that's really nice. I think remember enemies in the I don't have a Superman slide. Do you? Oh, I only look at what the Which neurology one? I'm so tired. Have you?
Yeah.
No. No.
It's the first PowerPoint, if it's a lot, right?
The muscle.
The muscle?
Yeah.
I got through like half of it last night and I was like, holy crap, this is so... I don't remember it
It's
being
like
that long.
180.
Yeah,
And this one's like 170, right?
the neurology
I
one.
think so.
They're both long, yeah.
And we have to do another neurology one for exam
On our own.
4 on our own.
Oh, for exam 4,
On our own.
which is Thursday.
Yeah, it's only 60 slides.
Oh, that's not bad.
On our video for the exam for Monday. We'll have to watch for that one with like help.
But he
I
has,
was hoping it'd be one that I can draw, because I don't know if it could really help, because you draw out and listening, you look back, like, you drew it, but it's like, especially these colors. At least for me, I'm like, I think I tend to be like, I don't know, because like,
Mhm.
I don't know if you're drinking neurology, but like, I think I'm like a kind of aesthetic learner.
Yeah.
So like, I write it down, like, oh, okay, I like, once I draw it, it's like, okay.
Mhm.
But I can't find
But
the
for this one, you just have to like understand everything.
Yeah.
that video really did help though, because,
The Duke one?
yeah, I watched the action potential one and the muscle one. They're like 20 minutes each.
Yeah,
I think-
potential one was good too.
Wait, show me it again?
Yeah.
What?
I have a sign-up thing.
Because that's both ones, like.
I mean, like, it's not good, like, if you don't get it, like,
Yeah.
but for like a second, round, I felt like it, like, helps. Is this the class?
No, I passed second semester now, yeah, college.
Okay.
Wait,
What's coming up?
what year are you?
I'm gonna be a sophomore.
Oh,
So you just need this one.
so you've done ortho?
So I did work right
How
now.
was it?
It was easy for me, but I like chem.
Okay.
Did you take it?
I got, but, what?
Did you take it like MCC?
No, I, go to therapy review
I don't
in
know why
Connecticut,
this is
but you
like-
have to get a
this
C
one
class
isn't
of anatomy to
Hmm.
pass.
Like
in
everything
the
else
nursing
is.
school, and I was
Did you
25
register
when I got
Yeah.
for it?
So they're making me retake the whole class.
Yeah, but I live in Market, so it's like I want to do that far.
That's weird.
Yeah, it's a macro.
Yeah, you can refresh it. Like, try.
Oh, yours is like opposite than mine.
Yeah.
That's why I was like, keep going like that. There it is.
Yeah.
Okay.
Can I erase this stuff, or you need to take pictures of any of this,
Oh
or?
my God, I so.
Oh, good.
I'm gonna take pictures of the top one, hold on.
You live in
I
Market?
emailed, yeah, I emailed, like, I think that Thea was the doctor, but I don't know, like.
You okay, Jeremy? That's...
Yeah, I'm good
Yeah,
now,
I live in
thanks.
Chatham.
Yeah.
That would be fine. Maybe not even.
There's another spot for the night after the night.
Yeah, I saw
And
last
everyone, like,
night, and I was going to like, take a look at that, like, I have to make sure that I reach it.
Do you know what
him Eric White. Yeah.
Is he gonna be a softball?
Yeah. I mean, it's a big one.
Wait, you go to where?
I go to Delaware.
Are you gonna be a softball?
Yeah.
You know Haley and Maria? She goes, but that, your school's so much bigger than mine.
Yeah.
Yeah, are you in a sorority?
Yeah, Ohio. They all sound the same.
I don't know why it's not.
So I'm trying to work it out because I need it.
No,
She's in this
but,
one.
you know, let me try to
What
register.
are the Greek letters so far?
I think it's- No. Yes.
I don't know.
I don't really know many people now. They're all so big.
I'm
What did you
going
say
on
your name
mine.
is? Eric White?
Oh, I forgot to show you the video. Shoot.
He's friends with like all my friends.
Really?
Oh, yeah, I know who he is, but
You do?
I don't, like, we're not friends.
Yeah, yeah.
But he's on Facebook, we have 100-something mutual friends.
Oh my god. Yeah, I know some of my really good friends in high school. What's your major?
Apparently don't know how to use a computer. Okay. Why is it doing that?
I don't know.
I don't even know how to do it. Like, why am I supposed to know on this whole thing?
What the heck? Where's content won't open?
Which is like,
Which is
oh, there we go. Okay. Okay. So then, yeah, I switched.
Oh my god. Hello? Heck. I'm clicking.
Yours looks different than mine for some reason. I don't know why.
It's so annoying. I can't get through it. It's really weird. It won't let me click into anything.
Oh.
Oh, wait, what? Continue? Oh, because this is where you are?
Well, I didn't do that, but
Oh.
but it would on mine. It would let me go to any of the weeks, which is how I watched that video.
Come on.
Okay, this looks so promising.
What?
Wait, what sorority did you say you were? Sorry.
Kaio. Okay, this isn't working. That's annoying.
When I go home, I'll see if I can.
Okay.
Maybe I can send it that way.
Yeah, let me know.
But I'm signed under mine. I thought that would help. But
Yeah, I don't know.
Is this still going, Noah?
Oh, I paused it.
Okay.
I was like, wait,
Okay.
we did the break there.
Are you familiar with Drexel University's nursing
Is
program?
that in New Jersey?
Drexel? It's in Philly.
No.
Oh, dang.
No.
Did it? I don't know if it did fall.
So, let's do, mostly anatomy, right? And I always try to get you guys in, see where we go, so I pop this up quite often, okay? Where are we, all right? Central nervous system, peripheral nervous system. What we're going to talk about mainly is somatic nervous system, dealing with the afferent, and we're also going to have somatic nervous system with voluntary and skeletal muscle. So we're kind of highlighting the areas that we're going to spend. There's going to be some tidbits of the other stuff, but not so much. All right, so you see where this slide is going to be popping up every time we're going to go over the nervous system. Because like I said, the nervous system I break up into 6 sections, just easier to manage. Okay, so just showing you how it all's broken up, and you can see it this way too. Okay, feels good. 4 slides out of the book. All right, we got 34 more slides to do. And there's another one, so we don't have to worry about that one. There's another one. You don't have to worry about that. See, it feels good, yeah? See what I'm saying? It's just like, ooh, it's not as bad as what you think. Okay, so the general anatomy of the spinal cord, and where is it? later on. Okay. So general anatomy of the spinal cord. As I explained to you, the spinal cord grows, but it stops at about 4 or 5 years old. Okay? So it only goes about 17 and 18 inches from your foramen magnum to about L2 in an adult. And it stops growing there. But the nerves need to continue to grow. Okay? The central canal is in the spinal cord. There's a hole in the center. And that's going to connect to those ventricles that we showed you in the brain, the Starship Enterprise. So we have hollow areas in the brain. The lining of that is going to make cerebral spinal fluid. But it's also going to connect to a very narrow canal throughout the whole spinal cord called the central canal, and cerebral spinal fluid will also flow through there also. Okay? There's 31 pairs of spinal nerves that come from the spinal cord. And there's certain points where they get enlarged a little bit. There's your brain, cerebrum, cerebellum, spinal cord. But there's a certain part in the cervical area where it gets a little, I'm going to exaggerate it though, gets enlarged. And there's a certain part of the lumbar area that's also going to get enlarged. We call these the cervical and lumbar enlargements. This is because we have a lot more nerves in here because it's going to go to our toes and to our fingers, where we're going to need more nerves to do the dexterity and a little bit of the toe wiggling. So there's a little bit more involved there, so we have this little bump because there's more nerves in those areas that eventually going to go out to those areas. Okay? Yeah, from C4 to T1 and T9 to L1. We'll learn about this more, I think, tomorrow with you. We'll go into it. No, Monday. Okay. Now some other things. Anatomy. There's something called the conus medullaris, or the medullary cone. That's where the spinal cord tapers off at L1. It looks like a little cone and pointy there. Then we have the corna equina. So I'm going to draw this closer up here because we're going to need to get to this. That point is the medullary cone, or the conus medullaris. Nerves are going to go out here. But soon, they're going to go down here. Causing a tail to occur here, of just nerves. This ends at about L2. But we still have spinal nerves for L3, L4, L5, S1, S2, S3, and so forth. We're going to learn, or you're going to read about the coverings, what we call the meninges of the brain. And there's 3 meninges there, 3 coverings. Something called the dura mater, which is a very tough mother. And then we have an arachnoid layer, which looks like a web, like arachnophobia. And then a very thin one, a thin mother, we call it a pia mater. And that's the one that's right on this brain. And it's also not just on the brain, it's going to all be on the spinal cord too. So the 3 coverings around here, to protect the brain, we have the same 3 coverings around the spinal cord also. And the pia mater is the one that's going to be on the spinal cord itself. I'm going to draw it in red for you. When it's on here, it continues downward. Until it reaches the coccyx, the tailbone. What it's going to do is this red here is just going to be pia mater. It's going to anchor the spinal cord so that it doesn't move up and down. There's no nerve in there, it's just this pia mater that becomes a little bit tougher down there. Then some of the pia mater is going to go outside like this. And it's going to anchor the spinal cord laterally to the vertebral column, to the vertebral foramen. So this way the spinal cord really can't move sideways or up and down. It's anchoring it all around, keeping like a spider web. Inside the spinal cord we have nerves. There's ones that are going to go up to the brain, and they're called ascending tracts, for obvious reasons. Since it's going up to the brain to get interpreted, it's got to be sensory. It's got to be afferent. Once the brain interprets what the heck that needle was, it's then going to send descending tracts through the spinal cord to wherever muscles it needs to do to either retract or to pet the cat that you're touching, whatever it is. Those are going to be motor nerves or efferent nerves. So the spinal cord is route 80. We have cars going east to west, west to east. We have nerves that are going to go north and south, south to north, right? It's going to go up and down. It's great. It really is a highway. There's a lot of nerves going up there. We call those nerves in the spinal cord tracts. Okay? So again, there's a spinal cord over here. It ends right there, sorry. Chorda equina is going down here, the horse's tail. And you'll have the terminal phylum, which is just the pia mater that's going to anchor the spinal cord to the coccyx. It doesn't show the denticular ligaments on the sides over here, but I got another picture that will show it there. So again, how the spinal nerves are being labeled over here is that the nerves are going to go underneath the vertebra that it corresponds to. For instance, here's the spinal cord. This is T12 vertebra. So the nerve, the spinal nerve that comes underneath there is going to be T12 nerve. It's going to go underneath the vertebra that it corresponds to. There's one exception, up here. We have 7 cervical vertebrae, but there's 8 cervical nerves. The reason why is because we do have one nerve coming above C1, and that offsets that. So in this case, it's the one that's going to be above it to be called up. Does that make sense? If you follow, you'll see. But there's a C8 there nerve. There is no C8 vertebra. And then from the T and the lumbar, then it just follows suit. It's the one underneath it. The spinal cord ends at vertebra L2. But the nerves need to continue onwards, causing this to be this horse's tail, the chorda equina. Chorda meaning tail, equina like equestrian horse. Now what's the significance of this chorda equina besides just the way the anatomy is? Well, when we do lumbar punctures, spinal taps, and epidural, we have to put a needle into the cavity. There's cerebral spinal fluid there. And we need to check to see, we got to draw some of that cerebral spinal fluid and send it off to the lab to see if there's bacteria, viruses, if there's anything like that in there, to see if there's meningitis or something like that. But the problem is we can't put the needle where there's a spinal cord. Because if you put a needle in the spinal cord, boy, are you going to go probably to jail and all, that's malpractice. Because you don't know the anatomy, okay? You're going to paralyze the person and inject something in there. So we got to go to a safe spot. And the safe spot is anything below L2. But we want to be safer, because some people might go a little bit lower than that. So we don't go anything above L3. The problem is that L3 to L4 is the most common place that we're going to put the needle. If we go down any lower, it's too low. There's a lot of fatty tissue there, a lot of muscle. It's hard to get there. So we got this narrow window to work with. They can go down one more. It's difficult, but they can do that. So there you're going to have the quadriquina. So are you concerned about hitting those nerves? Not really. Let's say this is where my palm ends over here is the spinal, that's where the spinal cord ends. But then where my fingers are, well, that's where the quadriquina is. You don't want to put a needle here. You're going to paralyze the person. Okay? But if you put it where the quadriquina is, look what happens if you put a needle here. They kind of move out of the way. Does that make sense? So that's a safe place to put the needle. It's not going to go into, if you have a bunch of raw spaghetti all over here, and you want to take a needle and stab it, it's going to push the raw spaghetti or the uncooked spaghetti off to the side, and it'll go right to the table, right? You're not going to go. What's the chance of you hitting into one of those spaghettis? It's difficult. So it's the same way here. It kind of pushes them off to the side.
It's not very dense. It's not very dense.
No, it's loose. They can move around. Absolutely. Not a lot, but there's space that you can put the needle and it'll just go off to the sides. It's safe. Okay? So don't worry about what I put here in pink and blue. But hint, make sure you know, never put a needle, a lumbar puncture, a spinal tap, an epidural, above L3. Never, ever, ever, for that reason. Okay? Okay, let's look at a cross-section of the spinal cord. Now, we have words here. Don't let the words scare you. It's pretty easy to manage. Tracts we already talked about. These are bundles of fibers in the central nervous system that either go up to the brain or they come down. It's root 80, basically. Then we're going to talk about gray matter and white matter. Remember, white matter has myelin around it. Would those be axons, or would those be cell bodies? Or dendrites? Myelin is around what part of the neuron? Axons. So, the horns, gray matter, that's mainly the cell bodies and dendrites. There's some axons there, but that's not where the bulk is going to be. The bulk of the axons will be in the columns, also known as the funiculi. And the nuclei are the cell bodies in the central nervous system. Take a cross-section of cervical spinal cord, the thoracic area of the spinal cord, or lumbar. You won't have to worry about identifying, but I'm just trying to show you, they're pretty much similar to each other. You have that letter H or that butterfly in there. The butterfly is the gray matter. And it's surrounded by the white matter. So your tracts will be over here in the white matter. So the gray matter is this letter H of this butterfly. So we could have unmyelinated axons in there. And then the white matter surrounds the H, which is really the myelinated axons that go up and down the spinal cord, going to or from the brain. So a few things. The gray commissure. Commissure, you're going to see this word often, means connecting right and left sides. That's what a commissure is. So the gray commissure is this area here that's going to connect the right and left side. Now in this picture, back here is posterior, in the front here is going to be anterior. The anterior white commissure is going to be this area right here. Makes sense, right? Not too bad. It's not significant, but you can have an idea where the posterior white commissure is. Posterior to the gray commissure. And then you also have the central canal that I talked about right there, that little hole that's going to contain cerebral spinal fluid, CSF. That's made from our ventricles up there.
Why is the anterior white commissure significant?
Things we're going to talk about, but things cross over there more. They don't usually cross over here. So we're going to talk about certain nerves will cross over to the other side. They don't really cross over on that side. The gray horns, pretty easy. There's the gray horns over here. This is the anterior horn, the posterior horn, the lateral horn. Not too bad, right? The anterior gray horn has motor function. The posterior horn, gray horn, is going to do sensory. The autonomic nervous system is going to be where the lateral is, and it also connects the two. The white columns are funiculi. Anterior white column, posterior white column, lateral white column. Not too bad, right? Then we have something else going on. You get the picture, right? You touch something. Okay? You touch something, you're going to send sensory this way. This neuron, its cell bodies will be located here. It's a unipolar neuron. It has one point coming out of there. That's where you usually see them. They're going in this way. Goes up to the brain to interpret, that's pain. Alright, so it goes ascending, so it kind of moves in here, and eventually goes in as a, kind of goes this way, and it goes up as a myelinated axon going up, a tract. The brain says it's hot. Figures out, organizes what muscles to contract to respond to that hotness. And then it's going to send descending fibers all the way down until it synapses here in the anterior horn. There's going to be another cell body here, and it's going to send it out to there to remove the hand. This is posterior or dorsal. This is anterior or ventral. This is what we call the dorsal root of the spinal nerve. This is the ventral root. Now, I only drew one neuron there, but keep in mind, there's thousands of neurons there that are touching on every part of your skin over here. Which means that you're going to have a lot of cell bodies located in this area, so it's going to bulge out. Does that make sense? Cell bodies are much bigger than axons. This is called the dorsal root ganglion. There is no ventral root ganglion, because its cell bodies are located in the anterior horn. If we destroy the anterior horn, how is that person going to present himself? Is he not going to be able to move? Is he not able to feel? Or he's not able to do both?
Where's that again?
The anterior horn. If we destroy this, is he not able to move, not able to feel, or not able to be doing both? Who says can't move? Who says can't feel? Who says can't do both? It's that you can't move. His green is fully intact. His brain is going to interpret. He can feel and he knows what that is. It's pain, it's pleasurable, whichever. The brain is then going to send fibers down to whatever parts, but if this anterior horn is destroyed, or destroying, or defective, you're not going to be able to send motor there, you're not going to be able to move. Does that make sense? You know what disease I'm describing? Lou Gehrig's, ALS. They can feel, they can't move. They can feel that fly, they can't swat it. Why is that important? Because if you're a nurse or you're a family member, and God forbid your mother or your father have this, hold their hand. They can feel that. Don't think that they can't move, they can't feel. They can feel. They need that compassion. They want to know that you're there, even if they're lying there and sleeping. This is what I'm saying. You're putting things together here and understanding how the disease works. This is, for some reason, this gets destroyed. We don't know the reason for that. But it's the anterior horns that get destroyed. They can feel, they can't move. You could hold their hand, they're not going to squeeze back, but they could feel your hand there. It's important you have that compassion at the bedside to do that. questions on that? See this thing over here? See this thing over here? Pretty easy to manage. Okay, there's another one over here. Fair game for the practical. Okay? Just showing you the different parts. Okay? We'll go more into it a little bit later. A few other things over here is the posterior median sulcus. It goes over here, and then we also have the anterior medial fissure over here. Just a couple things. But why is this picture? Let me see. Yeah, why is this picture misleading? What's wrong with this picture? Yeah.
The dorsal root median is on the side.
It's what?
It's above the
Yeah, right here. Look at this picture. See, I pay attention to pictures in your books. See, the dorsal root ganglion does not have sensory and motor, as this picture depicts. It's this way. See, what's happening here is this is the sensory, and the dorsal root only contains sensory. Here's the ventral root. It only contains motor. This is your spinal nerve, which contains both. All spinal nerves are mixed. But the roots are not. And you should know what's in each of the roots. Okay? So basic terminology and nerves. Sensory, this should be old news to you guys. Sensory, bring it into the body, right? Into the central nervous system. The five senses, position, that kind of stuff. Motor, information from the brain to outside the body. Okay? Some cranial nerves may carry both. All spinal nerves carry both. If it's both, we say it's a mixed nerve. Afferent nerves have sensory input. Efferent nerves, motor output. Same. S-A-M-E, right? My mnemonic for there. You see the glass, sensory's going in. Just the way you saw over here, the green. Brain interprets, you got interneurons there. This is one neuron telling another neuron what to do, right? We talked about neurotransmitters and things like that. Then this is going to tell another nerve what to do, motor. All spinal nerves are mixed, 31 pairs. And just what I put up here, you got the dorsal nerve root or the posterior nerve root. Either one is fine, okay? Dorsal root ganglion is there. There is no ventral root ganglion. Just showing you over here. All right. This one, I don't know why I didn't put it before, but here, this is where it shows. So you're looking at the dorsal root over here, and the ventral root is kind of bigger. You can see there's two kind of roots to it. We're showing you the ventral root here, the dorsal root here. You can also appreciate the denticular ligaments, which I didn't show you. These little lines going this way, these red lines going on the sides here. There's a denticulate. That's pia mater over here. So it anchors it laterally. All right, just you touch something over here, sensory going this way, motor going that way to your muscle. All right, just trying to show you the columns over there. And this is a close-up of this right here. So here's the dorsal root ganglion. I only put one nerve in there, one cell body. But they're showing you two cell bodies. But in actuality, there's thousands in there creating a bulge in that area and calling that the ganglion, the dorsal root ganglion. Ganglion is basically where you're going to find cell bodies, just coalesced together. So now you can appreciate, we showed you kind of this before, if you got this disc that's going to bulge and press on the nerve, depending on what part, it could be the whole thing, it could be just the ventral roots, it could be just the dorsal roots, depends on how bad the bulge is, but that's going to, you're going to figure out what the presentation would be. Anyone here Guillain-Barré syndrome, GBS? No? Guillain-Barré, you'll hear it when you get into your medical professions. It's not an uncommon disease. Usually happens about 1 or 2 months after a viral infection. What happens here is that macrophages, certain white blood cells, are going to invade the myelin of the peripheral nerves. So out here, right, this stuff. And you get this myelin that starts getting inflamed and pressing on the nerves over there, all right? And a partial demyelination occurs, slowing down the slowing down the action potential, so to say. What happens with this is that they usually get weakness and tingling, pins and needles, in the furthest distance from your spinal cord. So it's usually your fingers, and we sometimes call it the glove and stocking disease, because it starts here and then gradually over a few days, it's like putting on a pair of gloves. Starts at the fingertips and it moves this way. Same thing with putting on socks. It starts at your toes, and as you put on your stockings or socks, it goes up that way. And it usually only affects the peripheral nervous system, not the central nervous system. Luckily, 80% of these cases recover in 3 to 12 months. I know a case where it actually resolved in they resolved in 2 weeks. But it's usually 80% of them, and it's usually self-limiting, meaning it's nothing to really worry about. However, if that's the thing that's happened to you, the first thing people are thinking about is stroke, right? You're thinking of something to the worst. And even the doctors are thinking the same way, too. So you got to rule out everything else, and the really only way to diagnose it is a rule-out process. You ruled out everything else, it's probably this, we're going to watch you, you could go home, but if it gets any worse, let us know. But it seems like it's starting from your fingertips and going this way. Eventually, as this is going this way, this will start recovering until it disappears. So it's called Guillain-Barré syndrome. If you know Andy Griffith, he had it, he didn't die from it, he died from pneumonia years later after GBS. But I try to always put some kind of celebrities on there as much as possible. And I haven't seen any celebrity other than him. You guys know who Andy Griffith is? Right? Old time over here, and then Matlock.
What kind of virus?
It could be, see, that's the whole thing is, sometimes you might not even realize you had a viral infection. You had the common cold. You didn't even think about that, and that was about 2 months ago. I kind of, and the doctor will ask, that's what I'm saying, doctors need to ask these questions. They might skip over these and just diagnose by test, but there is no test really for this. But you put it all together. Did you have a stomach ache or some virus that you took off from work, from your stomach? You just had a bellyache or something like that. Did you have a runny nose? In the springtime, they're getting these symptoms in, August. Getting a cold in June, they would remember that. You know what I mean?
Is that kind of like how Bell's palsy is suspected?
It can happen from that, but there's a lot of other reasons that would cause that. We'll get into facial palsy, but there could be other reasons that could be pressing on that nerve. But that is one. An infection could have been the reason for that, and that's also another self-limiting thing. Again, your face droops down, you're thinking stroke. You got to rule out the big stuff, and hopefully it's one of these other things. It's scary for both the doctor, the patient, the nurse, and so forth, because you don't know what's happening. You're thinking the worst. Your face you smile and you smile like that. There's something going on here. Is that something that wouldn't be so worrisome, or is it something that it's a different treatment for both? Okay. So it's Guillain-Barré syndrome. Okay. Nothing really to worry about, but for them it's something. And you start feeling these guys. You can't. And it's also dealing with for muscle too. So you can't grab onto things. You can't do certain things for those. If it's going to last a year, it's that kind of thing. We've got to monitor to see if it's getting better. Very fast about a reflex arc, but we'll spend more time talking about it on Monday. Reflex arc is an involuntary muscle reaction, okay? And it basically is this whole thing. It goes this way, but it doesn't go up to the brain. Okay? It just stays within here. There's another neuron in here that connects the green with the red. It stays within here. Even though it goes into the brain for a split second, sometimes it takes a little bit longer. You've all done this. You stub your toe. Isn't there a delay? You're like, okay, the pain's come. There it is. All right, there it is. Ow, ow, ow. Right? This is delay. I mean, that's an obvious one. But keep in mind, if you just hit a needle or whatever, there is a small, like a second delay. Here, there wouldn't be. It's a reflex. It happens very fast. Doesn't need to be interpreted. All right, and we'll talk about different reflexes later on. So a spinal reflex is going to go right to the spine, and that's it. For a cranial reflex, it has to go to the brain, but not to be interpreted. It's because there's no spinal cord up there. So it just goes up and goes right back out. All right? You touch the white of your eye, you got the blink reflex. Something like that. Okay? So that's what a reflex is. Sometimes they can be hazardous if you're working with amphibians. Okay? Well, let's do a little bit of Frankenstein. Okay? Not going to test you on this. It's just something we did years ago, back in the 40s and 50s, but we can't do this now. You'll see why. Okay? This is how it works normally. All right? A frog. I touch a frog on the right foot. It says, these are reflexes. It says sensory over here, and then it connects to the motor, and then the same leg will kick down. It's a reflex. Does that make sense? All right? So you touch here, just the way I did over here. You touch on this foot, goes this way, and then the same foot is going to kick down. It's a reflex. Okay? Now, let's do Frankenstein. I'm going to cut here. Attach this, and I'm going to cut here. So I'm cutting at the B and the A. And I'm going to, God bless you, attach it this way. You see it? Give it a moment. Let it get yourself oriented. Right. So this is a dummy. It's not going anywhere over here. You can see why we can't do it now, because people are too much of this animal activist kind of stuff. All right? You know what I'm saying? Can't do it now, because after this, we send them off to the graveyard, okay? We can't send them out like, walking around like this. It's not going to happen. Use them for frog legs, but, So now look what's going to happen. You touch the right leg, it goes this way, but it's going to cross, and then the left leg kicks back. You see it? Touch the right leg, sensory goes this way, but we made this little connection here, and it goes on the opposite side, and it goes right down to the left leg, and it kicks down the left leg. Now, I'm not going to test you on that, but if you understand this, then I know you understand the concept of this.
Okay, so what would happen if you touch the other leg?
Nothing.
Nothing, they won't feel it. It'll be numb. If I cut this off, you see this green over here? If I cut off this, it's not going to be able to get... It's severed. Another reason why we can't do this is the leg won't be able, they can't hop. All right? I guess we could donate them and somebody can adopt one of these jumpless fish or amphibians, but too many animal activists now. They can't do this. But it's a good learning experience, right? All right, questions on that? All right, that's all I want to do for you today. All right, so the rest of the time, it's like an hour and a half or so. The rest of the time, we look at, it's up to you. If you want to go, if you want to look at models, you want to look at the bones over here, I'm here, utilize me. For the rest of the semester, I'll come in at 5 o'clock. Yeah, 5 o'clock. For anybody who wants to come in to look at bones, muscles, ask me questions, that kind of thing. All right? But please, if there's an exam that day, for your own sake, don't ask me, can you go over something, and then, or ask me the, like, questions. It's not because I don't want to do it, I just don't want you to, you studied really hard, and then I say, well, this is all wrong. You know how you're going to perform on the exam in less than an hour? It's like, I did it all wrong, and you start having a complex, right? It's like one or, if there's a couple of, tweaking up stuff, that's no problem. The only time that you won't be able to come in is on the day of practical exams, because this room will be filled. But I'll make sure that the room across the hall, where Emily and Noel were at, across the hall, that'll be open. I have a key for that door, and I'll make sure that that's open if it's locked. So you can always go in there and study. There's a whiteboard in there. If you want to draw things with each other, that's fine too. So I have no problems with that. But I'll always be here. I got here like 5 after 5, but around that time. All right? You want to look at phones? I have no problems with that. Okay? Any other questions, concerns? So no test tomorrow, right?
Wait, yeah.
Lab quiz.
Oh, the lab quiz. Oh, okay. Yeah, the lab quiz, what we'll do, make sure you're here at 6:15. All right? And I'll have this room set up, but I'll be here at 5 o'clock, and I'll set it up. I could put, like, a skeleton or a box of bones in that room over there, and you can take a look at that while I'm setting up in here. All right? Any questions? It's the best I could do, and hopefully everyone got my email about what's happening with the Learning Center, the hours and stuff. So you could go over there and knock off that. So we got a lab quiz tomorrow.
That's just 20 questions.
That's just 20, yeah. Oh, and that's, yeah. So that's basically, there'll be 10 stations over here. I got 2 rest stations and stuff, so you have little breaks. But a good example of this is, as I said, I'll let you in. You'll have, I may have this here. One question might be, I'll put that in my time. One question might be, like a vertebrae. I might say, what is this bony structure called, number 1? And I know you can't see in the back, but, that'll be the superior articular facet. Number 2, I might say, what is this called? Be specific. And you would say acetabular. Or I might say, the bone that articulates here forms what kind of joint? You could say synovial, you could say ball and socket, you could say diarthrosis, okay? Might say, what sex is this? Right? And you would say male, okay? So you'll have, in this case for the quiz, you'll have 2 questions for each real station. So 2 times 10 is 20 questions. You'll have a minute for each station, 30 seconds for each question, and then I'll say switch. And then you'll go to the next station, and maybe there'll be a femur there, and there's 2 more questions. And then I'll say switch, and so forth, until everyone's all done with it. That'll probably take, like 20, 25 minutes or so. And then we're done then. Then we'll go over it, and then we'll go to the other thing. The practical exam is going to be 50 questions, so 3 questions on each. It'll be a minute and a half for each station. It'll be exactly the same, except it's also going to include this also. So one station will have that. Old stuff for you. Bone, I figure it's not bad. You remember this? Shit, right? So, periosteum and this whole area, and osteon. So, I'll leave that out if you want to take pictures of that or whatever. And that's it. That's not too bad. Yeah?
Can we, go back to the station and see,
No. No, just one time around. Yeah. I'm finding more people being able, if they do that, most students usually say, I have some people say, I don't want to go back, because here's my test, believe it or not. And I have other ones that mark things, they had it right, but they changed their answers. And, so. But there's enough rest stations there. I'm going to put some rest stations there where you can actually make sure, you cross your T's, dot your I's kind of thing. So. Okay? Sound good? Other things. That's it. After tomorrow, we only got 2 weeks left. It's good, right? It's almost over.
Hey, after today, we have a test every day.
Let me ask you, because I'm teaching the same exact thing right the week after, and I have no problems doing that. That first exam that you had, which was on cytology, chemistry, and intro to A&P, how would it be if I actually gave that test the first week on Thursday, instead of you having that 3-day weekend studying for it? Does that help things?
It would probably show you more how the course is.
Yeah.
Like, having those extra days, I was like, oh, okay, sweet.
Yeah.
And then you have like 4 other exams that week.
Right. So you think it's better that, I shouldn't tease them thinking that there's going to be, pretty much a weekend before each exam. That's what I was thinking before. It just worked. You see, last summer, they didn't have a 3-day weekend. They only had 2 days. And I did do it on that Friday. But I also had a lot more failures for that first exam. I know, that's the thing. That's why I gave the whole week. They have it just happens that, and it's falling the same way. You had a 3-day weekend, and they're going to have a 3-day week in the first one because it's 4th of July. So it just worked out that way. So it has its pros and cons.
It's hard to have an exam without a weekend. Like, I feel like I need to.
Yeah. And that's why, it'd be nice if I could do it, but I'm afraid doing it, like, for you guys, I did it for the first time, and you were too comfortable, you were getting used to the fact that, well, he's probably giving us even though I didn't say it, but I don't want you to think there's a weekend.
Yeah, but we have the schedule. We have the schedule, so we know that.
You have the schedule, but I don't want people to procrastinate until the weekend. I want them to do a little bit each day. Not saying you guys did that, but I have a feeling, you had that temptation of doing it for the weekend. But if I have an exam on that Thursday, there's no temptation. You're forced to do a little bit each day.
So sort of more, like if you had a chemistry report or something, or more complicated.
Yeah. And last year when I actually did the chemistry for them. You guys had the video. The video was okay, though? You prefer videos than me lecturing? Yeah.
It's a nice follow-up.
Yeah.
Yeah.
I think the advantage is that you could pause it and rewind it.
Yeah.
That I would like to do in classes.
Yeah. Yeah. I guess in the future I'll do a little bit more of those. Yeah. All right, well, still debating on it. It has its pros and cons to do it on that first Thursday. I just don't want people to procrastinate and say, I got the long weekend, I'll study during that weekend. But it's not going to be like for each exam. Like you're seeing, 3 exams on each. And if I do that, then I can almost push every exam up one day.
I think the rest is not, so it's not good at all.
Oh, true. Although next week you got 3 biggies. Yeah. And it's like, what do you do during the weekend? What do you study? Bones? Or do you study the test for Monday? Or do you Yeah, I don't know how you guys do it. I give you full credit. You guys are all doing these tests. Yeah, really, all I'm doing is guiding you, but I have no idea how you do it. I would not be able to, I'll be honest with you, I would not be able to do this. So, no, I couldn't. I know the questions I give. They're hard. I would not. But I teach, I'm saying it's the same exams as, spring and fall, so it's just, Karen's in. And she's still on transcription translation, you said? But they're tests on bones.
Yeah, well, she had a practical on both today, but a test on bones.
Yeah. I don't know. No, that's a femur. Greater tubercle? Oh, no, I'm sorry, trochanter. No, tubercle, that's it. Yep. I'm sorry, I'm thinking trochanter on the femur. But it's very similar. If you know the upper extremity, lower extremity is similar.
Oh, yeah, okay. But this, yeah.
Yeah, that's why if you get enough, well, you can see it on here.
I mean, I need to look around.
Yeah.
I need to look on over here.
Here's the greater tubercle, here's the lesser.
Okay, yeah.
Yeah.
I'll take that one.
Yeah, that's fine. Dance with him.
I don't know what app she was talking about, but I found one that shows pretty well.
And does it explode? You can move it around up
Yeah.
different colors?
Then it's free.
Yeah,
I think it's nice.
Oh, there's a lot of them out there, I can't. Essential skeleton, yep.
Yeah,
Mhm.
it's pretty good. It's just,
Yeah.
everybody.
Because you could highlight it and, yeah, it's
Looking on playing on my phone at home.
no, it's, you're studying. Nowadays, people can do that. You have I did it differently. I had to visualize things. That's how I came up with all mnemonics. I didn't have all this other stuff.
It's a little tough from the drawings, right, from that.
Mhm, yeah.
That you don't have with you.
Yeah, the drawings are not
But
that.
it doesn't show the dimension and some of the things that makes it look a little.
But if you
But
had,
it really kind of makes up for it.
But if you use those packets, like, once you know what the bone looks like,
Right.
then you just,
So what I did is I was looking around looking at work, and then I've got 3 minutes here and there, I'm looking at it, I'm just going over it, flipping it over, and then I'm trying to pinpoint everything where they are, right? Then I'm going to go, oh, okay, now it actually makes sense why it's
Yeah.
that, because it's separate.
right.
How to go about printing in
There's no print, here,
anywhere here at school.
library?
Library.
There's,
Library.
printer and, isn't there a printer, and I never use it, but isn't
Well, I
there
think
one
it's closed
that's
now.
in between the 2 buildings where they've got that study room?
Oh, next to the cafeteria?
Yeah, there's a sign about a printer.
Yeah,
I don't know that it's maybe just a copier, but.
you gotta check up there,
I
yeah.
don't know how to how do I send it, to the printer or whatever? How do I hook it up to my laptop or whatever? Because my printer at home doesn't have color, and I'm trying to print the pictures of, I got pictures of the bone.
Yeah, I don't know if they got print, I don't think they have, color up there.
Okay.
I think one of the better things to do if you're gonna do like certain things, like I wouldn't do like this, you wanna do color, you know what I'm saying? You could adapt it, 'cause this is just a waste. Staples.
Yeah.
Yeah, if you want it in color, but you could turn it into, let's say, 6 per page.
Yeah.
I know, most libraries, the library near me, Muscular, has it prints regular prints, 5 minutes. So that's cheaper, and for color probably is and that.
Yeah.
So if you go to the local library, it's printing at the library. Can I ask you a question on this? About the anterior, superior, iliac spine?
Yeah, that's what I would, or Staples, something, but just pick and choose what slides you want to color. You don't need to put everything in color, but once...
I went on the internet and I, got pictures of every single bone and, all the little things and that.
Do you have a smartphone or no? Tony, can you show her that, and it's free too. This is another way, it's not a printout, but it actually, you could do things with it. So where's anterior and where's posterior?
So wait, anterior and the front. Would anterior be here?
Yeah, what's gonna be difficult, what you're doing,
Yeah.
that's the right hip, you got the left hip. Okay, so you're doing, and it's fine.
Yeah.
So what's gonna happen here, I'll show you. All right, so, acetabular. That.
Right.
So this is the left hip.
Right.
So this is anterior, that's posterior. Okay? This is the anterior superior iliac spine.
Is that anterior, inferior?
Uh-huh. What's this? Not this, this.
That posterior, superior,
And,
posterior, inferior.
correct. So if I was gonna label it, see it?
Yeah. I'm kind of having trouble with this part of it. This, looking at like skeleton.
I won't ask you anything in the orbit.
You won't?
No.
Okay.
The only one is, like you see what a greed is?
This?
Yeah.
Yeah.
And then you also see where the red,
Yeah.
that's about it,
Okay.
which is the lacrimal and ethmoid. But, I mean, I tell you, yeah, that's really it, but because the frontal, the yellow is easy to see,
Right.
the maxilla, the orange is easy to see, it's all the same, and the zygomatic. I mean, deep is gonna be the purple, which is the sphenoid.
Right, okay. And then, we were having trouble with the weight of the sphenoid.
Let me get the sphenoid, I'll show
When I
you.
look at it, it makes sense.
Yeah, I'll show you.
It's like, oh, yeah. Yeah, you could do that at work, but like, the arm's going up the part.
Interested in like doing like quick to each other before we move. Like, I'm just trying to figure out like what to like without having to come in.
What I did is mostly what I felt the bone, I felt my bone pointing apart. I felt my bone pointing apart. You would replay it and touch yourself.
Oh, you have No. I mean, see, go back to 4,000. Think that, I'll ask like the third question. I mean, that could
Alright,
be,
then watch me take the next class and see if you can figure it out.
so I have your permission to,
Sure.
all right. I'll take the challenge.
Challenge
And then I'll
accepted.
ask questions. All right.
For the grade.
Don't exaggerate it, though. Be
No,
natural, yeah.
No,
Okay.
it's a little exaggerated for me.
Okay.
Yeah.
Yeah, I'll keep an eye on that. No, I just want to show you, I don't know where the sphenoid is.
I just think of it like, that little thing in the back.
Oh, here it is. You know the skull here?
It has to go to the body. Right, that's the name,
You see how this, that's a sphenoid, it's like a bat, right?
Yeah.
Sits in there like that. You see it? You see it? Okay? That's the lesser ring. is the greater wing.
The way I kind
Oh,
of
like this thing.
That's one wing there,
Okay.
and there's a greater wing here.
Okay.
And then you have this little cup over here.
Right.
It's a bony cup that the pituitary gland sits in. That's the cell of turcica.
Okay.
So, here, so this is gonna be your lesser wing. The greater wing's over here, cell of turcica.
So you would have that skull?
I won't have this out for you, but if can you see it like this? It's just easier to teach on that.
But like you could label that part, like you would have it.
Yeah, if I say, well, I could point to this
Yeah.
area here, like, have a label right here and say, what is this bony structure and the bone that it belongs to? So you would say lesser wing of sphenoid.
Oh, okay. I was confused because I thought that only, like you were only gonna have this one skull, and I was like, how?
No, I could do the inside of the skull, yeah. And what I'm saying was to explain, so I won't take off all this. But, you know, sometimes it's easier to teach on like that. Like I could also, if it also,
Like you wouldn't label like the sphenoid from the orbital cavity, would you? Like,
no, I wouldn't ask you that. But it's not too bad. You see the yellow in the eye?
like when it's
Look at the yellow.
color-coded, you can tell.
Right. So you have an idea of where it is. So now you can see the sphenoid,
Yeah.
the yellow, and you see the greater wing and lesser wing.
But like from the outside, you can't tell like the lesser wing, right? Those
No,
are
you
the-
can't see,
those
it's
are the
inside.
greater wing.
Right, the lesser wing is up here, yep. So if that helps.
Okay, yeah.
Again, this won't be on the test, but it does put things in perspective. All the red is the ethmoid bone. You can see on the sides over there, you can see it in there too. You can see it in there.
Right. And then which of the cervical vertebrae, like the two...
Sorry, thank you.
The one, which one's on top again?
Atlas and axis.
Oh, Atlas.
It goes in alphabetical order.
Oh,
Atlas is up on, and holds the world.
right.
Yeah, the
Like,
it looks like an O.
like this. Is that the best way to like how what an like if you got just one cervical spine, you know, it's the atlas, like what would you look for to like be able to know?
It has no spinous process.
Oh. Everything.
See it?
Yeah.
Yeah, it's going here.
Behind.
Yeah, so it's not like it's people who came in. I was looking at the earlier, and I...
Here's the three cervicals.
That one would be the atlas.
Oh, but that. Oh, yeah. And that's just our regular one.
It could be C3 or C4, but it's definitely cervical because there's three holes there. But usually, not all the time, but usually the spinous process is 5', it's forked.
That's what I was looking at, because I don't
Yeah.
right here. Like,
Yeah, and when you get down lower, they're not as forked.
Do we have to know if it's 3 or 4?
No, it isn't cervical. The only ones you need to know is C1 and C2. Those are the exceptions.
So what are we looking at for like the, phalanges and that and the ankle wrist? Like, would it just be like,
Carpal.
give us like a hand and be like, what is
Mhm.
this? What is this? What is this?
Yeah, identify what this is.
It wouldn't be like a carpal bone on the table.
What's that?
It wouldn't be like one carpal bone.
No, I'm not gonna say, no, it's the way it is that I showed you, no, I wouldn't do that for you. You guys are not ready for it, that's medical school, that's where, that's, some teachers like to do that, they'll do like the sphenoid here, I think you guys could pick up sphenoid, but there's enough to go around, I'm not gonna, although carpal is very close, I think in the fall, I think I should start asking to know the different carpals, because all the other teachers are doing it, so I'm watering it down, I'm dumbing it down for you guys, believe it or not. And then there's, They've all, I mean, there's mnemonics that are all floating out there. There's, you know, I won't go through them, but there's always mnemonics to help you out with a lot of these bones.
Wait, what's the true and false?
The false pelvis is above the pelvic brim. So here's the pelvic brim, or arcuate line.
Right.
Above it is the false pelvis.
Right.
Below it, it's like a funnel, so the true pelvis is really going to dictate if a baby can go through there.
And then I was having trouble finding the
That's this. See, when you sit down, you're really sitting like this. There's the tailbone's gone, but you're sitting like this. So you're sitting on like a tripod. The two ischial tuberosities and the tailbone.
Okay.
So it's three things that you're actually, you know what I'm saying?
Okay. Oh, okay. Okay, that makes sense. So it's just and then tuberosities are...
Yeah. So 11 is the ischial tuberosity.
Okay.
Yeah.
And then one would be ischium?
Right. The blue is the names of the bones. The pink are parts of those bones. So that's ischium, pubic bone, and there should be three blue on here. Yeah. And that's the ilium.
Okay.
If you pointed at, like, the superior,
Articular facet or process, yeah.
would you just put that, or would you have to say, like,
It would be in the question.
Okay.
I might say, what is this bony marking, what is this bony structure, and just answer what that is. Or I might say, what is this bony structure and the bone it comes from.
But you wouldn't have to say, like, left, or like,
No,
which one?
no. Unless it says which side, but the only ones is the ones I noted. No, that's,
Are the pelvic brim and ischial spine the same?
no, ischial spine is the point. No, this.
Oh, sorry, I'm having trouble with the picture.
Yeah,
Oh, okay.
the point there, yeah. Yeah, if you go to the next, no, sorry. Ischial, yeah,
Right, okay, okay.
yeah.
Could we call it the pelvic brim instead of the...
Arcuate line?
Yeah. Or, okay.
Yeah, if I should say, what separates the false and true pelvi, then you'll say the pelvic brim or arcuate line. Or I might say the arcuate line, what's found above the arcuate line?
Or don't fall.
Right, that's what I mean, so you need to recognize, you can put down whatever you want to spell, but you need to still know what the arcuate line is. Noel, don't want you to, am I being...
Oh my God, stop it.
Oh, I don't know. It's still red. What does that mean?
That's like a whole 35 minutes worth of... Oh.
So you gotta rewind and...
I'll figure it out.
Was it a tape or an MP3?